My name is Abby Lute. I am a postdoctoral researcher at the Woodwell Climate Research Center, which is formerly known as Woods Hole. It's based in Massachusetts. And I got into climate, snow, glaciers, hydrology because I was inspired by the 3 years I spent in New Zealand. I was going to school while I was there, but I spent pretty much every weekend in the mountains, just exploring and marveling at the landscapes. And there's such a diversity of landscapes there, and it really made me want to understand what is it that makes these places the way they are? Like, what is it about the climate? What is it about the geology? How do these things interact? All the pieces together. And so that inspired me to go to grad school to study mostly a focus on snow and climate in mountains. Rock glaciers are very similar to glaciers, with normal glaciers, ice glaciers, the ones you typically think of. They, just like glaciers, they are bodies of ice that flow down slope under their own weight, so it's gravity driven. And what makes them different from normal glaciers is that they have this rocky debris layer covering the ice surface, or almost all of the ice surface. Depending on the type of rock glacier, you could also have rocks mixed in with the internal ice, or it might just be pretty solid ice with rock on top. And there's a few different kinds of rock glaciers. Some are derived from glaciers. So you might imagine as a glacier recedes, we have less ice in that glacier, but some of the sidewalls that are around the glacier or the moraines might start to collapse, and some of that debris, the rock debris, might fall on top of the glacier. So that's one way that we could get a rock glacier. The other primary mechanism is we start with a pile of talus, which is just a pile of rocks on a slope in the mountains. And if we get enough snow accumulation on top of that, and then the snow melt water goes down between the rocks in the talus and refreezes, eventually you can build up enough ice that you have movement. So if there's enough weight, then the ice moves, and that can become a rock glacier as well. So those are the two primary kinds. When we think about the differences between a glacier and a rock glacier, it's kind of this continuum from like a pure ice glacier that's completely ice to a debris covered glacier, which means it's a ice glacier that has some debris on top. And then at the far end of the spectrum is a rock glacier, where the ice surface is almost entirely covered in rock. So you can think of the difference between a glacier and a rock glacier as being a matter of this ice to debris ratio. And another thing that makes rock glaciers different from normal glaciers is that they tend to exist in more arid climates. So, for example, in the Western US, we think of glaciers being like in the Cascades of Oregon and Washington, the Olympics in Washington, Glacier National Park, a few other places scattered around. In contrast, rock glaciers can be found throughout the Intermountain West in a lot of our high mountains, including the Rockies in Colorado, Utah, Wyoming, central Idaho. There's quite a few. So there's a much greater geographic spread of the rock glaciers, and they're typically in these warmer environments. And what makes that possible is that rocky debris layer. So, somewhat counterintuitively, that layer of rock on top of the rock glacier actually insulates the underlying ice from the air. And that allows these rock glaciers to exist in places that would be too warm for a normal glacier. Rock glaciers are really great rock movers as well. So these rock glaciers are typically located at the base of a rock head wall, and that head wall will gradually let loose rock debris, and that lands on the rock glacier. And the rock glacier then, as it moves under the force of gravity, it transports that rocky debris downslope. So it's moving debris in mountains, and at the same time, similar to a glacier, that weight of the ice and the rock is carving the mountain. So you may have heard of like U-shaped valleys that glaciers form. Rock glaciers can do similar things. Rock glaciers are typically smaller than glaciers, so these are going to be smaller erosion features, but it's a similar process. So rock glaciers typically move pretty slowly, so on the order of maybe a meter per year. So if you were sitting next to a rock glacier waiting for it to move, you'd probably be sitting there for a long time before you noticed any movement. And that we can compare that with a typical glacier. And those, I mean, there's a wide range, but we're talking on the order of tens to hundreds of meters per year of movement in a typical glacier. And you can think of that as being explained by the mass of the ice and rock. So that mass is what's driving the movement, and glaciers are typically larger than rock glaciers, so they typically move more quickly. And so the deformation of that ice is dependent on a few different factors. One of the main factors is the temperature of the ice. So glaciers or rock glaciers in warmer environments tend to move more quickly than those in really cold environments. So there's a couple ways that rock glaciers impact climate and microclimate. One is through a local effect on temperature. Well, all the effects are fairly local, but temperature is one of the effects. And so you can imagine a rock glacier being, it's as if somebody left a refrigerator door open, because you have this massive amount of ice just laying there on the landscape. And so it's providing a local cooling effect. The other primary way that rock glaciers affect microclimate is through moisture regulation. So just like a glacier or a snowpack, these rock glaciers melt when it gets too hot. And so that's typically in the late summer, often after the seasonal snow has melted. And so these rock glaciers are providing this late summer moisture, and that comes out in the form of small streams or wetlands in front of the rock glaciers. So the main benefit that humans get from rock glaciers is through this cold summer stream flow that I described. So rock glaciers are providing a really unique source of water in those hot, dry summer months, typically after the snow has melted. And that's important for fish. It can also be important for agriculture. So I know in some parts of Chile, farmers depend on the rock glacier melt for irrigation. So rock glaciers provide actually really excellent habitat. Maybe you wouldn't think so, considering it's ice and rock, but they actually provide great habitat for small mammals, insects, and plants. So small mammals like pika like to hang out on or around rock glaciers because it's a cooler area. And then the wetlands that I described before, they provide this source of cool water in the late summer that is really great for insects and for plant species. And there have been several studies that have shown that rock glacier environments, the environment right around the rock glacier and the rock glacier wetland, support greater biodiversity than adjacent areas that don't have rock glaciers. So rock glaciers, like glaciers or tree rings, provide an excellent record of past climate. And so you can take an ice core from a rock glacier just like you would from a glacier, and you can observe the layers in the ice core and look at the gas contents and the thickness and the debris and get a sense of what the past climate was like. And so we can use them to observe trends over time. And another way that rock glaciers indicate changes in climate is through their dynamics. So the deformation of the ice in the rock glacier allows it to flow downhill, and that deformation rate depends on temperature. And so as the air temperature warms, so does the ice temperature. And that allows the rock glacier to flow more quickly. You can imagine some honey that you put on a plate at an angle, And if it's really cold honey, it's probably not going to go very far. But if it's warm honey, it's going to be running down the plate. It's the same with a rock glacier. And so one of the challenges of that is that means that rock glaciers can flow away from their sources of rock debris, which is that rock head wall up in the cirque, and also their source of snow, which eventually forms ice. And so we can get these detached rock glaciers, which become dead rock glaciers because they don't have that source of snow and ice. Yeah, if it's not moving, then you can't really call it a glacier anymore. So one way that rock glaciers contribute to local variability is through that temperature and moisture regulation that I mentioned before. So they're creating these cool pockets in the mountains that have late summer cool water. So that's supporting extra biodiversity in those areas. And then the other way is through their erosion of mountain slopes. And so one really neat effect that rock glaciers have on a larger scale is on the shape of entire mountain ranges, actually. So if you imagine a mountain range, maybe it's oriented east to west. So one side is facing south, one side is facing north. And most of the rock glaciers would be forming on the north side because it's shaded. So let's say all the rock glaciers are on the north side. And those rock glaciers are slowly eroding those slopes on the north side. And so they're forming these little cirques right at the ridge top. And so over time, the net effect that you would get is the south slope of this mountain range would rise from the valley to the ridge fairly gradually. But on the north slope, you would have these big cutaways near the ridge line. So you'd have a much steeper topography near the ridge line on the north side. And so we see these patterns throughout the West, and rock glaciers are really shaping what the mountains look like. They're very sneaky. Like you might not even know they are there. They're like ninja rock glaciers. And that's because they're covered in this rock debris. So if you're walking by one, it might just look like a pile of rocks, unless you know what you're looking for. So before I started studying rock glaciers, I was up working in an alpine basin. I would go up there several times a week and work on some instrumentation. And it was only later that I found out that every time I went there, I was walking by a rock glacier. So you kind of have to know what you're looking for. And what you're looking for is this kind of bulbous shape. So if you imagine that honey on the plate at an angle, and the honey, it's going to have a steep angle at the front where it's the leading edge of the honey drip. So it's going to look kind of like that, but with rocks on top. So tricky to spot, but pretty exciting when you find them.